Hello friends, in this session we are going to find out potential energy of an electric dipole which is placed inside uniform external electrical field. Okay, so let us see how to find out. First of all, we will consider a electrical dipole which is placed inside uniform electrical field. Now, how to indicate uniform electrical field? When the field lines are parallel to each other, then this electrical field is considered to be uniform. So this is nothing but what? Uniform electrical field. Okay. Now we will take a dipole, electrical dipole inside this electrical field. So we have a dipole inside the electrical field. Okay, and this is positive charge Q and this is negative charge Q. Okay, the distance between these two charges is nothing but 2L, right? What is electric dipole? It is nothing but what? Two charges of equal magnitude but opposite polarities are separated by a very small distance, and that particular arrangement is called as electrical dipole. So this electrical dipole is placed inside the external electrical field. This electrical dipole is making an angle of theta with the electrical field. Okay, the axis of the dipole is making an angle theta with the electrical field. Now what will happen the moment we are placing this electrical dipole inside the electrical field? This charge, right, electrical field is always from positive to negative. So this positive charge will get repelled from this side and will get attracted towards this side. So that means this will be the force, this is the direction of the force which is acting on this plus Q charge. And what is the magnitude of that force? The magnitude of that force is given by F is equal to Q into E, right? Okay. What about this charge? The minus Q charge will get attracted towards positive and will get repelled from negative. So that means this is the direction of the force which is acting on plus Q charge. So this is F is equal to, what is the charge? Minus Q into E, right? So that means this is nothing but what? The force. So how is the nature of the force? Is electrical field uniform? Yes, it is uniform. So that means this E and this E will be same. Okay. Is the charge, the magnitude of the charge same? Yes, the magnitude of the charge is also same. That means the magnitude of this force is also same. Okay. But what about the direction? The direction are what? Opposite. Right? So you imagine that this is the electrical dipole, and one force is acting in this direction, another force is acting in this direction. What will happen? Right? It will tend to rotate in this direction, right? In this direction. So something, a physical quantity which tends to rotational motion is called as torque. So that means torque will be acting on this object. What is the equation, the expression for torque? Torque is given by tau vector is equal to r vector cross f vector, where r is nothing but what? The perpendicular distance between the two forces, right? Where f is the magnitude, f is nothing but what? One of the force. So what is the in this particular case, what is the magnitude of this torque? The magnitude of this torque is given by magnitude of R into magnitude of A, F into sine theta, where theta is nothing but what? The angle between the force and the perpendicular distance. So in this particular case, I can say tau is equal to R. What is R? R is nothing but what? 2L. So 2L into magnitude of one of the force into sine theta, this angle theta. Okay, so F, what is F? F is equal to what? Q into E. So what is tau? Tau is equal to 2L into Q into E sine theta. What is Q? 2L into Q? It is nothing but what? Electrical dipole moment. Electric dipole moment. So tau is equal to P So we have tau is equal to 2L. What is the magnitude of F? E Q into E. Q into E sine theta. So tau is equal to, what is 2L into Q or 2Q into L? It is nothing but what? Electric dipole moment. So P E sine theta. So this is nothing but what? The torque which is acting on this electric dipole moment. Okay. Now what I am doing is I am applying external force, right? Exactly opposite to this force, exactly opposite to this force, exactly opposite to this force, and then displacing this, I am making some angular displacement of d theta, right? In what direction is the torque acting? This direction, right? This direction. So torque is acting in what? This direction. I am applying external force in opposite direction, here also in opposite direction. So what will happen is I am applying external torque in opposite direction and making some angular displacement in opposite direction. Okay, so this external torque tau into a very small displacement d theta will give me nothing but a very small work done for this small angular displacement d theta, which is nothing but what? dw, right? And this work then gets converted into potential energy, gets stored inside the system in form of potential energy. Why? Because the moment I am applying external torque, the tendency of this charge is to move in opposite direction, is to rotate in opposite direction. That's the reason why the work done will get converted into potential energy. So in order to find out the total work done, W, I require to integrate dW. Okay, let's say for example, initially the angle that this dipole is making, the angle of this dipole with external electrical field is θ1, and I am making a very small angular displacement from θ1 to θ2. So I require to integrate this dW from θ1 to θ2. So the total work done dW is equal to integration from θ1 to θ2. What is dW? It is tau d theta, right? So W is equal to integration of θ1, θ2. What is tau? Tau is given by P E sine theta, right? Okay, into d theta. Okay, now P, electrical dipole moment, is it constant with respect to angle theta? Yes. Electrical field, obviously it is uniform, so it is constant. So W is equal to PE, integration of sine theta from theta 1 to theta 2 d theta. Integration of sine theta minus cos theta. So W is equal to PE, okay, minus cos theta from theta 1 to theta 2. So W is equal to P into E, upper limit first, minus cos theta 2 minus plus cos theta 1. So finally we have W is equal to P into E cos theta 1 minus cos theta 2. Now, since we have got this equation for the potential energy, we will take some special cases into consideration and then understand. So, the equation of work done or the equation of potential energy was given by, which we have already derived, P into E cos theta 1 minus cos theta 2. Now, in case I assume that theta 1, that means the initial angle of the axis of the dipole along with electrical field, if theta 1 is equal to 90 degree, that means the dipole is held perpendicular to the direction of electrical field. So, if I am assuming that theta 1 is 90 degrees, then cos 90 will become equal to 0. And the equation can be written as W is equal to P into E into minus cos theta 2. So the equation is W is equal to minus P into E cos theta 2. Now considering this equation, we will study some special cases. Okay? Special cases. Number 1, if theta 2 is equal to 0 degrees, that means what? Theta 1 is the initial angle and theta 2 is the final angle. That means initially the dipole is like this, the positive charge is over here, negative charge is over here. So this is theta 1, which is nothing but what? 90 degrees. We have already considered theta 1 is what? 90 degrees. And then theta 2 is nothing but the final angle, which is equal to 0 degrees. That means the dipole has been rotated like this, right? So that means the positive charge is pointing here and the negative charge is over here. So in this case, the positive charge will get attracted towards the negative terminal. How is the electrical field? It is always from positive to negative. Here we have positive charge, it will get attracted towards negative. Here we have negative charge, it will get attracted towards positive. So that means in this particular state, the electrical dipole is completely at stable equilibrium. Yes or no? Yes. So this is the position of stable equilibrium, and in this position of stable equilibrium, let us find out what is the potential energy. So potential energy U, which is nothing but what? Work done. Work done and potential energy is what? One and the same thing. The work done will get stored inside the system as potential energy. So this means work and potential energy is what? One and the same thing. U is equal to minus P into E cos 0. Cos 0 is what? 1. So U is equal to minus P into E. So this is the minimum potential energy which can be stored inside the object, which can be placed inside the electrical dipole when it is in stable equilibrium. Okay. Okay. If theta 2 is equal to 90 degree. So theta 1, that is the initial angle, was 90 degree, and theta 2 is also 90 degree. So what will happen? Cos 90 in this equation, cos 90 minus cos 90, which comes to what? 0. So work done is equal to what? 0. And because since the work done is equal to 0, potential energy is also equal to 0, right? So this indicates that if let's say for example I am bringing electrical dipole moment, electric dipole from infinity in external electrical field and placing this dipole in perpendicular to the external electrical field, the work done will be equal to 0. How is it so? Because positive work done will be positive work will be done by plus charge q, and negative work, same amount of negative work will be done by minus q charge. So that is the reason why the total work done becomes equal to 0 and the potential energy of the system become equal to 0. Okay. Now let us take third case. This was second case. Third case. If theta 2 is equal to 180 degree. Now what do you mean by 180 degree? Theta 1 was like this, plus charge was here and negative charge was here, right? I am rotating this from theta 1, that is from 90 degree to 180 degree. So this angle, this will become 180 degree. That means the positive charge is now pointing towards the positive terminal of the electrical field, and the negative charge is now pointing towards the negative, right? So that means here there will be what? Repulsion, and between this there will be again what? Be repulsion. So that means I can say that electrical dipole moment is now anti-parallel to the electric field, right? So that means this is an unstable equilibrium, and since there is a huge force of repulsion on the either of the side, the potential energy will also be equal to maximum, right? So this is the position of what? Unstable equilibrium, where the potential energy is maximum. So substituting in this equation, what do we get? W is equal to minus P into E cos 180. What is cos 180? Is minus 1. So we have minus of P into E into minus 1. So W is equal to P into E. Since the work done is maximum, the potential energy U is also maximum, P into E. Right? Okay. I hope you have understood the session. Thanks a lot.